Welcome back. So, we discussed a problem of an adiabatic turbine and we noticed that the change in the enthalpy, the specific enthalpy was around 400 kilojoule per kg. This is one of the typical numbers that you will get in steam turbine calculations. In fact, let us look at a reasonably general delta H that one can notice in steam turbines. For example, most steam turbines nowadays would operate around 150 160 bars. Of course, some are now in the supercritical range, but let us say the standard ones are around 160 bars, which is 16 megapascals, and the inlet temperature would be around 550 560 degrees centigrade. So, at this condition, the specific enthalpy of the steam, if you look up the steam tables, would be around this number, and let me just write it. It is an approximate number, please do not look at it exactly. 160 bar, 540 degrees centigrade, the H would be around 3412 kilojoule per kg. Now, most steam turbines would have an exit at saturation near 30 to 35 degrees centigrade, because that is where you get the cooling water and you can check up what the enthalpy at that state would be. Of course, depending on whether the turbine was operating at isentropic conditions or with some isentropic efficiency, the enthalpy would be different, but you would realize that the exit enthalpy, if you look up the table, would be somewhere between 2500 to, let us say, 2550 or even 2600 kilojoule per kg. This is at exit roughly. So, if I calculate an Hi minus He, let me assume it is 3400 at the inlet and 2500 at the exit. This would be of the order of 900 kilojoule per kg. This is the kind of delta Hs you expect in modern turbines. This is steam turbine. Now, if you look at, let us say, gas turbine, in that case the H can be calculated using Cp delta T, and m dot Cp delta T would give you the inlet enthalpy, and m dot Cp times Ti minus Te would give you the change in enthalpy in such turbines. So, Cp, let us say the gas turbine is operating with air, for Cp for air, and I will just write down approximate values, it is around a kilojoule per kg, and delta T that you get in gas turbines could be anywhere between 200 to, let us say, 500 degrees centigrade. So, you see that even here the delta H, which would be just Cp times delta T, would be between 200 to 500 kilojoule per kg. What about Ve and Vi? So, we will look at the numbers that typically we will see. Typical velocities one can expect are anywhere around 10 to 20 meters per second. Sometimes, of course, if you have nozzles, at the exit of nozzles you get reasonably high velocities, but at the inlet and exits of turbines we have anywhere between 20 to 50 meters per second. So, let us just have a look at what these numbers mean. If I have a velocity, let us say V, it does not matter whether it is inlet or exit, let us say it is 10 meters per second. So, is Vi squared or Ve squared, V squared by 2 is 100 by 2, which is 50, but realize that this number is meter square per second square, which is just joule per kg. And if I want it as kilojoule per kg, you would have it at 0.05 kilojoule per kg. If you go to 20 meters per second, well, V squared by 2 is 200 joule per kg, which is 0.2 kilojoule per kg. If you move to 50 meters per second, this would be 1.25 kilojoule per kg. If you move to 100 meters per second, this you would move to 5 kilojoule per kg. And only if we are talking of around 300 meters per second, you notice that we move to around 45 kilojoule per kg, where it starts making a difference because our delta H is of the order of 400 to 900, 45 then is at least 10% of it. Otherwise, even at 50 meters per second, it barely makes a difference in our calculation with delta H. So, this was all regarding Ke, and you realize that this is a particular velocity V. So, Ve squared and Vi squared, if they are of the same order, you realize that the difference would be even more negligible, and hence one does not consider these. Let us look at Pe. Let me assume, just for simplicity of calculation, that G is around 10 meter per second square rather than 9.8. For turbines and compressors and pumps, the height difference at most could start anywhere between much less than a meter to even 2, 3, 4 meters. If I take a meter, that is the height difference between Ze and Zi, you will go as this is Gze minus Zi. I could write as 10 1 meters. This is assuming Ze minus Zi. So, this you realize is going to be only 10 joule per kg, which is 0.01 kilojoule per kg. Now, one could have sometimes in some boilers around 10 meters, in which case this number would be 10, this would be 100 and this would be 0.1. Only very rarely in some boilers, where depending on how you take the inlet, you could probably go up to even 100 meters of difference, in which case this is 1000 and this is only 1 kilojoule per kg. By far the difference in potential energy in such systems can be reasonably negligible. Of course, in nozzle the velocity at the exit matters a lot. In fact, the entire delta H comes out as the change in kinetic energy, but for turbines one can safely assume that you will get values around this and you will get values around this for the potential energy, which is reasonably negligible, and hence such quantities you realize can be neglected when you are dealing with turbines. But it is always wise to first calculate delta H, figure out your assumptions. If you have the area at the inlet and exit, you have the densities, because for steam you can get the densities looking up the steam tables at the required conditions. For air it is very easy to get the densities given your pressure and temperatures, and you find out what your velocities are, see if it is making any difference. If it is making a difference, include it, but initially you can always go ahead with the assumption that these are negligible, and that is something that you can always start with if no information is given regarding these quantities. So, now we will consider a more general problem in the next snippet, but that is it for now. Thank you.